For the bipolars, you can do the same thing. And the most important parameter for a bipolar is usually the beta. This is also explained in all the books, and usually can find this kind of plots. But let's take an PNP, and let's plot the beta versus VB, because it's the easiest way. And for this, you have to apply a certain voltage on between the emitter and the collector, and a voltage between the base and the emitter. Now, to calculate the beta, as you for sure you know that the beta is collector current versus the current into the base. And for this, what you have to do, you have to vary the base to emitter voltage, keeping the constant voltage between the emitter and the collector, and you will obtain a plot something like this. This is the VBE, and this is the beta. And as I said, since the beta is the ratio between two currents, you have to plot both of them and then to make the ratio between them. You can do it directly in the waveform plot, or you can do it as a formula in the simulator, or whatever you like. But you will obtain something like this. Is something that is flat between certain VB voltages. And this is important because you need to have your operating point here somewhere into this plateau. The same thing can be seen in a different way, because now we have the plot versus the voltage, but let's plot it versus the current. If we take exactly the same setup and we plot not the beta, which is ratio between currents, but directly the currents, collector and base, versus VB, we get something like this. VB on the x-axis, current into the base, and current into the collector, and we get something like this. Now, this flat region corresponds with this plateau. Oh, I forgot to tell something. This is a logarithmic plot. If you take it linearly, it will not look like that. But if it's logarithmic, you'll see that this is actually looking like a straight line. And since these lines are parallel, ratio between them will be a constant number, which means that you are on this plateau. Usually when you design something with bipolars, you have to be sure that you are here somewhere in the plateau, or let's say in the constant slope region. If you are here, already you have some troubles because the beta will not be constant. It will vary a lot, so better to avoid. And this is well known in the books, is usually called the gamma plot. And it's done with this kind of setup very easily. Of course, this is a setup for PNP, but you can build it easily for the NPN. As you know, you can flip the schematic. Another way to characterize the beta is actually to plot the beta versus collector current. You can manipulate the plots so that you put current into the collector on the x-axis, but still is not the best way. I know another way to do it. I think it's easier and more. I think it's also more intuitive. And let's put here on this paper. We can rebuild the setup so that we have now again the bipolar with the current into the collector. This time is the current that we vary. This is what we sweep in the simulator. but then we have to keep constant the voltage, collector to emitter. And for this we have to create a loop, because it's not that easy when you change the current into the collector. So a way to do it is actually to use an op-amp that has two inputs, an ideal op-amp, for example, or a voltage controlled voltage source, or an ideal op-amp is the same thing in the simulator. You can connect the negative here and the positive to a power supply, to a plus and minus, and this one can be connected here. And of course, to keep this constant, you have to put another supply here. Here is ground, for example. Here is, for example, 5 volt. Here is, let's say, 5 volt. And what you obtain with this? What you obtain is that since you create this loop, you have, as you know, any op-amp has the same voltage at the input of the inputs. So the voltage here is equal with the voltage here. So whatever voltage you had here will be the same here. So means that if you have here a constant supply, a constant voltage source, then this constant voltage source will actually be emitter to the collector. So this collector to emitter, or emitter to collector, whatever you want to call it. And the base to emitter voltage will be generated automatically by the loop, by the op-amp. And why is this important? Because if you want to sweep the current into the collector, then it will not work if you keep the VBE constant. So the VBE voltage will have to change. And but of course, the collector to emitter voltage has to be constant. So that's why you have to create this kind of loop. And what plot can you obtain with this? You can get something like this. Current into the collector on the x-axis, because it's the value that we want to sweep. And here is the beta. Of course, the beta is the same thing like before, is the current into the collector divided by the current into the base. Of course, in this setup you have to save the current into the collector and the current into the base. The current into the collector, you already know it because it's the value that you want to sweep. You have to save the current into the base. Now, if you plot this, you obtain something like this. It's flat and then it's dropping. Of course, this is a logarithmic, while this one is linear. Again, you have the plateau, so you have to be sure that for a certain collector to emitter voltage and for a certain collector current, you are on the plateau, so means the beta is constant. As you see, any bipolar has a range where the beta begins to drop rapidly if the current into the collector is too big, or if we take on the other side, on the gamma plot, is actually here when the beta is dropping, or here when the beta is dropping. Actually, it's the same characteristic but seen in a different way. Here is versus voltage, while here is versus current. The normal operating point here somewhere. Would be nice to have it here. So yeah, as you see, there are different methods to characterize the CMOS and also the bipolar. And this is useful, especially in the beginning when you learn about the new technology and you are not sure about the characteristic of the transistors, and you want to be sure that you understand the effects and the way the transistor is behaving. Sometimes you have a nonlinearity, sometimes you have a certain drop or a slope that is not as it was in the previous technology. So you have to really check this kind of things. And also it's useful to have these setups around you, because you can easily go back and resimulate a certain operating point to know what is happening in case that you see something that is abnormal.